All right, this is AP Calculus AB, Session B, second semester, so to speak. This is Unit 2, Lesson 2. We're talking about the definite integral and definite integrals and antiderivatives. What I want to address here is something called a Riemann sum. We introduced in the last lesson the idea of subdividing a area problem into rectangles and summing up the rectangles. Okay, we're going to carry that a little bit further. We're going to carry it into the concept of limits, and we're going to come up with something called the limit definition of an antiderivative or an integral. Okay, just like in derivatives, we had a definition, a formal definition, which was the change in y over the change in x, and taking the limit as delta x as the h goes down to 0. We're going to have a similar definition here. Just for the sake of review here, the derivative of f of x, as you recall, is the limit as h goes to 0 of f of x plus h. This is the standard definition. There are some others. Minus f of x over h, right? Recall that. We're going to have another limit definition for antiderivatives or integrals as well. Okay, and it's going to come from this concept of subdividing into rectangles. Okay, so let's say we have some function. We'll call it f of x. And it's defined on the domain from a to b. Okay, defined on the interval from a to b, and that one's not straight, so let me fix it. Okay. Okay. All right, and we subdivide this into sections. So we have a function f of x on the domain from a to b, and we're looking for the area under the curve between the values a and b. And so we divide it, okay, into segments. Now we can divide it into any number of segments. Okay, in this case, I'm going to divide it on the whole number lines, but this is just for the sake of illustration. But I can divide it into any number of segments here. Okay. Now I want to formalize that a little bit more. Let's call this the width of this bin, we'll call it delta x. The Greek letter delta often stands for change in, right? So delta x, or change in x. And if I divide this into n partitions, then the width delta x, if I divide it evenly, is b minus a divided by n. Think of it, the highest minus the lowest gives me the range. Divide that range into n partitions, so to divide it by n. So we're going to remember that. Delta x is b minus a divided by n. Okay? And so now, and let's put that over here, delta x. Okay. So now I want to find the area of one of the rectangles. I'm just going to pick a rectangle in the middle somewhere here. Okay? And I'm going to pick this one here, and I'm going to use the right rectangular approximation method. So I'm going to take my value off of the right hand side. Okay, and we'll call this a sub I. A sub I. All right. The height at a sub I is f of x, f of a sub I. Okay, a sub I. So this is the ith rectangle. If in this drawing I have the first rectangle, the second rectangle, the third rectangle, the fourth rectangle. So in this drawing that would be the fourth rectangle. But a sub I, it can be any number, right? And the area of the rectangle is delta x times f of a sub I. Does that make sense? Length times width, right? And it all depends on, oh, well, let's insert now b minus a, right? So delta x is b minus a over n. And this is f of a sub I. Now let's delve into that a sub I a little bit. A sub I. How do I determine what a sub I is? Well, it's a plus a plus, well, in this case, if this is 1, 2, 3, if I is 4, then it's a plus delta x times 1, 2, 3, 4, right? So a sub I equals a plus delta x times 4, but 4 is just a number, a whole placeholder I was putting in for I. So a sub I equals a, we'll call it a sub 0 if you like, plus delta x I. So basically we're taking the left boundary and multiplying the interval that we're counting by the index number of the rectangle. So let's change that again here a little bit. So the area of the rectangle is b minus a over n, f of a plus delta x I. But what is delta x? Delta x is b minus a over n. Okay, so that's the area of a single rectangle. A single rectangle. Now, the idea of a Riemann sum, I always forget, does Riemann have, yeah, it has two ends. Riemann. It's German, and I don't pronounce it quite right. It's Riemann or something like that. Riemann sum. I just say Riemann sum. Okay. So the Riemann sum is the sum of all the rectangles, but we're going to use a little bit of summation notation, sigma notation for summation. So from I equals 1, because the first bin is right here, we're going to take the height of the bin right there. So from I equals 1 to n, like if this were the first bin, second bin, third bin, fourth bin, fifth, sixth, seventh, I divide it into 7 bins. I sub 7 would be the last one. It would be up to 7. But we're going to do it up to n bins, right? The sum from I equals 1 to n of b minus a over n times f of a plus b minus a over n I. And I think the book puts the b minus a over n at the end. And that's fine. F of a plus b minus a over n I times b minus a over n. Okay, and that would give me the summation of any number. If I let n be 50, then I would be dividing it into 50 bins. If I let n equal 100, I'd be dividing it into 100 bins. Okay, in the diagram I divided it into 7 bins. But now we're going to formalize this a little bit more. We're going to say, let's take the limit of this sum as n goes to infinity. As the number of bins, as the number of subdivisions gets infinitely large, each slice becomes infinitely small. And so we have kind of a going to 0. The area of each rectangle is going to 0, but the number of rectangles is growing to infinity. So we have this race to infinity and to 0 going on at the same time, and they counter each other. And we're taking the limit as the bins get super, super, super small, it approximates very closely the true area under the curve. And this then is the definition of a definite integral. Okay? So here we go. Let's rewrite this here a little bit. The definition of a definite integral, the integral from a to b of f of x dx is the limit as n goes to infinity of the sum from I equals 1 to n of f of a plus b minus a over n I times b minus a over n. Okay, and I believe the textbook put in delta x instead of b minus a over n, and then told you what b minus a over n. I prefer this notation a little bit better. It identifies all the variables that we need to know. All the variables over here are over here, except for n, which is an index that is going to infinity, or which is a number that's going off to infinity, and I, which is an index that counts from 1 to n. All right? Now, that's enough, but let's use it. All right? Let's use it. So using the definition of a definite integral, can you take the definite integral or find the definite integral of a function? Okay? Let's copy this here, and let's do a problem. Okay, right. Oh, wrong there. I need a new slide. Okay. Oh, I thought I copied. No, I didn't copy. All right. See if I can remember. The integral from a to b of f of x dx is the limit as n goes to infinity of the sum from I equals 1 to n of f of a plus b minus a over n I times b minus a over n. Look at that. Write it down like that a few times until you get it. You're going to get some questions about this. Let's now use this to find the integral from 1 to 3 of x squared dx. Okay, the integral from 1 to 3 of x squared dx. Okay, using this notation here, this is the limit as n goes to infinity of the sum from I equals 1 to n. Okay, f of a plus all that is x squared. So a, that's a is 1, plus b minus a, 3 minus 2 over n times I, squared, because that's f of x. F of x is x squared. b minus a over n is 3, not 3 minus 2, 3 minus 1 over n. Let me fix that. 3 minus 1. And let me fix that plus sign while I'm at it. 3 minus 1 plus. Okay, there we go. Little simplifying in algebra here. Let's do the limit as n goes to infinity from I equals 1 to n of 1 plus 2 over n I squared times 2 over n. Okay, and now let's square that. Okay, and I'm going to forego writing the preliminary stuff for a minute here. So squaring, square a binomial, first squared plus 2 times the first times the second, 4 over n I, plus the last squared, 4 over n squared I squared, times 2 over n. Okay, and then we're going to distribute the 2 over n, so we get 2 over n plus 8 over n squared I plus 8 over n cubed I squared. Okay, and now we're going to bring back the limit here. All of this. Okay, limit. Sounds like a frog. Rivet, limit. Okay, got a little close together. All right, and so now we need to find the limit. Now there are some summation formulas you need to be aware of from your pre-calculus class. The sum of a constant, okay, from I equals 1 to n is the constant times n. The sum from I equals 1 to n of I is n times n plus 1 divided by 2. And we're not going to derive these. These are simply given as a fact. And the derivation of them is interesting. I equals 1 to n and is worth studying. I squared is n times n plus 1 times 2n plus 1 divided by 6. And in case you need it, the sum from I equals 1 to n of I cubed is n squared times n plus 1 squared over 4. Okay? All right. And the other thing is that any constant can be factored out. Okay? So the sum of a constant, so let's take the limit as n goes to infinity. Okay, the sum from I equals 1 of 2 over n, it distributes over addition, is 2 over n times n. 2 over n times n, because remember it's kn and this is k. 2 over n is k. Okay, 8 over n squared is just a constant here, so I can factor it out, and this is the sum of 8 over n squared actually, times the sum of I. The sum of I is n times n plus 1 over 2. Okay, and 8 over n cubed, the sum of the I squareds is n times n plus 1 times 2n plus 1 divided by 6. Okay, and then we expand the limit as n goes to infinity of 2 over n times n is 2. 8 over 2 simplifies to 4 over n squared times, distribute the n squared plus n. Okay. And the next one, 8 over 6 simplifies to 4 over 3n cubed times, okay, and multiply n times n plus 1, you get n squared plus n, and then times 2n plus 1. I've already done this here, so I'm going to skip ahead a little bit. 2n cubed plus 3n squared plus n. Okay, and now distribute the limit as n goes to infinity of 2 plus, now distribute the 4 over n squared. The n squareds cancel, leaving 4. 4 over n squared times n is 4 over n. 4 over 3n cubed times 2n cubed is 8 over 3. 4 over 3n cubed times 3n squared, the 3's cancel, leaving 4 over n. 4 over 3n cubed times n is 4 over 3n squared. Okay, now a little bit of review. What happens to a fraction as the denominator grows uncontrollably off to infinity? The fraction goes to 0. That's a very important principle in solving limits. So 4 over n goes to 0. 4 over n goes to 0. 4 over 3n squared goes to 0. And this whole sum is 2 plus 4 plus 8 thirds, or 6 plus 8 thirds. 6 over 1 plus 8 over 3. Multiply by 3, 18 over 3. 18 over 18 plus 8 is 26 thirds. Or if you wanted a mixed number, it would be 3 times 8, which is 24, and 2 thirds. 8 and 2 thirds. And you can check with Desmos here, or your TI-84, which also does definite integrals. Do IMT in Desmos. 1 to 3 of x squared dx, 8 and 2 thirds if you like, or as a mixed number, improper fraction, 26 thirds. Okay, so it does work. it is long, and there's a couple of things you need to remember, and so some of these need to be committed to memory. This limit definition needs to be committed to memory. I would say you probably want to memorize the I summation formulas from constant up through I squared. You might possibly end up with an I cubed on the AP test. I'm not sure, but that might be worth considering too, but at least through I squared. All right, and this has been a long video because it's an intense topic.